Okay, so let's share. Okay. All right, have you seen this one? The textbook? Hello.
Yes, sir.
Yes, I'm share. Okay, so textbook here is the Logital Rule for the form of the type infinity over infinity. So this large over large. So we've covered this one. So just show you example from here. So math computing. Um, Here we have x to the e to the x. Okay, so John use derivative. Look with the rule, take derivative of 1x, that's 0. Okay, so let me just show you. X to the okay. So this is large over large. So we attempt to use Logital rule. That's the reason we compute the derivative. So there's 2x, this is e to the x remaining, x. And again, this is the form of the large over large. Okay. So another attempt of Logital rule. We compute the derivative. And now we can compute the limit because this is 2 remain constant, e to the x that's going to be large. So that's the limit is 0. And by Logital rule, f this one equal to the previous, and this means the limit exists, and then another application of Logital rule, we get the answer. Okay, so this is a twice application of the Logital rule. Similar thing, if you deal with x to the cube, for example, e to the x, and we know this is of the form large over large. Okay, so an attempt to use Logital rule is computing the derivatives of the x squared is the x, right? So, but then by the previous one, you have square over e to the exponential. So that's going to 0. Total by this one. Okay, so look, the rule give you. Okay, so basically you're using let's see, first Logital rule, second, third. So 3 times applications of Logital rule. And it is similar. I won't compute this one. Okay, by that's going to be 0. Okay, by applying Logital rule. So what does it mean? That means if um, you have polynomial over exponential. And x is large, right? So this always gives you 0. All right. So even the polynomial is large, but exponential is even much larger than polynomial. Okay. So then uh, it's much larger than any polynomial. We have some notation for this one. Say x, when x large, x squared is larger, much larger than x. This is much larger than x cubed. This means but this is much larger than exponential. Okay, so this is what we call the rate of growth. So you're like comparing rate of growth. Rate of growth of the x to the n, the rate of growth of the e exponential. Exponential is always wins in this case. It's much larger. Okay. All right. You can check out another. On the other hand, let me just complete this one here. Let's see. This one here. With x going to infinity with the ln. Right. X, so what we get here. This is a form of large over large. Ln is large when x is large. This is polynomial. Okay. Uh, let's see. So we attempt to use a Logital Rule. That's why I take the derivative of both numerator and denominator. Okay. So here we get this is large. This is 1 over large. So this is small. So the limit is always 0. And by Logital Rule, we get this one. All right. So that means Ln is always much smaller than any polynomial. So in general logarithm. Than polynomial. Okay, so in the sense of rate of growth, you see this is, we have log, the lowest. Polynomial is much larger than log. but exponential is much larger than polynomial. Okay, so you're comparing three large things, but then you can see that the right one, the exponential, is uh, much larger than the polynomial. Polynomial is much larger than log. Okay. All right. So that's a little bit intuitive, but that should be what you need actually later on. And you have an idea how large is the stuff that you see. All right. So let's another. All right. So you have another indeterminate form of 0 times infinity, means small times large and large minus large. Okay. So why these two are indeterminate? Okay. This is small times large, and this is large subtract large. And why are those indefinite forms? All right. For this one here, 0 times infinity, I would like to uh, take an analogy with this. Is like the uh, let's see, how should I say this one? Oh, or this one better. Infinity minus infinity. Say uh, Superman and Batman pulling ropes, okay, on each sides. Okay, so that very much depends on the situations, on the conditions at that day, at particular time. Who's fitter at the time? Okay, so it's going to win. So this is indeterminate. This is small times large. Very much depend on how small and how large. Okay, so the question is a so the question is how small, how large. So they are indeterminate. Okay, so uh, let's see. The first thing is that Logital Rule does not apply to uh, for these indeterminate form. Okay, it's not, I would say, directly applies. Okay, so let's see. So what we can do. So what can we do for this kind of problems? All right, so let's take one example. Yeah. Let's do this one. So let's check the form here. And so this is x going to 0, so that's 0. But ln of x to the 1000. So ln of large is large. Okay, so what we're going to do with this one. All right, so let's write this down as this one. This is not a Logital, but an attempt to write this down as x. Right, so this is an attempt to rewrite the problem as a ratio. See, let's check this one here. What you get here. When x is large, then this goes to zero. Let's see. All right, x is small. X is small. Let me correct this one. Okay, I should correct this one. Okay, when x, x is small. So x is small, but ln of x small with power 1000. So really is really small. Take the ln. Recall that ln is this. So this limit is negative infinity. Okay, we call that one. So here we have so it is large but in terms of negative. All right. So what we have here, this is infinity, and this is 0. Okay, but this is not in definite form. Okay, because large over small is large in a way. So no Logital rule needed. All right, let's see. That's not a good example. Let's take the one that really cosecant 1 over sine is all right. So this one, x squared times cosecant squared. Cosecant squared x. Okay, so this one is 0 times infinity. So small times large. Cosecant is 1 over sine. Sine 0 is 0. So this, okay. And we write this uh, as a ratio. But cosecant is 1 over sine. So you have this there. So this is going to 0. Okay. Now you see this is um, a small over small. Then you can use Logital Rule. 2 sine x cosine x. And now using the let's see what you have here. This is also 0 over 0. Okay. So you can use another L'Hopital rule, attempt to use L'Hopital rule. You get 2 over the derivative of this, 2 sine. Let's see, this is cosine plus sine times. Right, so that's limit is now 1. Okay, so limit exists, then that equals to this one, and by that L'Hopital go to this one. Okay. Okay, actually from here, you can compute this directly. Because this is there. And this limit, you know this limit. This is special trig limit. All right. So this shows you that L'Hopital rule does not always simplify, but it may give a complicated thing, complicate things. So recalling that special trig functions is may help you simplifying things. Okay. All right. Another example. So let's do with the with that subtraction. With subtraction, so let's do, for example, this one here. Which one is subtraction? Oh, yeah, right. X going to pi over 2. When you plug in pi over 2, that's 90 degrees. Then this is a 1 over cosine. Cosine pi over 2 is 0. So this there. Okay. All right. So let's attempt to write this down as a ratio. Let's see. Once it has in a ratio form, then you might want to apply L'Hopital. 2. Tangent is what? Sine over cosine, and this is 1. Subtract 1 over cosine. Okay, so this is actually cosine, so sine x minus 1. All right, so let's see. This has the form of 0 over 0. So the L'Hopital rule is might be justified here. So take derivative, cosine, negative sine, right? Okay, cosine is 0 and this sine is 1, right? So the limit is 1. All right, hold on. That's words. Start with. So the limit is 1. Okay. The limit is 0. Okay. So this justifies you to use L'Hopital rule. This equals to the above. And this equals to the, no, this is not L'Hopital. This is L'Hopital. All right. So that's 0. So the idea is to rewrite the limit as a ratio, then applying the L'Hopital rule. As a ratio. Then attempt to use L'Hopital rule. Okay. All right, let's go back to the textbook. Now, the last thing is the indeterminate form of this one, of this. So 0 power 0, infinity power 0, 1 power infinity. These are all the indefinite form. Okay. Let's see. Okay. Okay. So this is times 3. 0, infinity 0. Okay, So what we going to do with this one? Let's do this one first. Um, say this is sorry, this one x um, one. Let's do this one. 1 plus 1 over x over x. Let's see first what kind of the indefinite form is this. So x going to infinity. So 1 over last is small. So this is going to be 1. That is 1 power infinity. So that's all. Okay. So what we are doing, what we're going to do here is not computing this directly, but compute this limit instead. Equals ln of 1 plus my ln. That's the key idea. Does it remind you of something? Applying ln? Have you ever met? You recall what kind of thing you apply ln first?
Is it easy?
This is the what you call log differential. You take derivative and then do the implicit differentiations first. Okay, so that's ln. All right, so let's simplify this one. If you apply ln, then the exponent will factors out. So it becomes x ln 1 over. Okay. So we work instead of this one, we work with the ln. Okay. And let's see, with this limit of y. Okay. So we work with this instead. So then this gives you, simplifying the ln, this gives you l. All right, let's see. So what we have here, this is large. This is, let's see, 1 over 1x is going to 1. And ln of 1, that's 0. So this is the form of there. Okay, so this is something that we recognize. It's indefinite form. Okay, so we attempt to write this down as a ratio. Okay, so as a ratio, this give you, keep the ln, but write as x is 1 over here, 1 over x. then let's do try to find this form. It's going to infinity, so that's 0, small. This is ln, it's going to ln of 1, that's 0 also. All right, so that's something that we can apply L'Hopital. So L'Hopital rule, we get derivative of 1 over x. Derivative of this is rather complicated, but that's times the derivative of this. 1 plus 1 over x derivative is, so then this cancel, and we can compute the limit. The limit is just plug in, this is going to 0. Okay, so 1 over 1. There we go. And by L'Hopital rule, this is equal to this one. Sorry. This is one. All right. But what we have is this limit of this ln. So the original problem is the e. Sorry, it's a without ln. So the applying the inverse is that e to be sorry, what we're going to say is that this should be equal to e to the limit of ln of 1. This will cancel. Okay. Because we compute this as 1, so all right, so that's the magic number that comes into action. Comes from this limit. Okay, so then let's continue this next week with just more problems of this indefinite forms, and continue with the with improper integrals. Okay, questions?
Sir, I have a question. Why did you put E in the last part?
All right, that's to counter of the ln. Right?
Okay, understood.
Okay, we apply ln first, and then at the end apply e, the inverse. Okay. More questions? All right, if not, we'll stop here. You will have a problem sessions later on Thursday with Kemal. All right, let's stop here. Stop. Stop record.